네, 네, 네. 네. 네, okay. 고맙습니다. Alright. Good. Hi, everyone. Welcome back. So today is the deadline for Form 2. Nobody cares? You better. Okay, let's continue. No. Okay. So it's going to be pretty colorful lecture today. Okay. Any questions? Yes.
In last lecture, you said about the contraction.
Yeah.
If just computer of operator.
Yes.
And I think that it's very non-trivial that the commutation relation of the operator is just constant for a free particle theory.
That's right. So good. The question is, we talked about contraction, and then we showed that the contraction is commutator of phi plus with phi minus, for instance. And the question, I think, is it a special that the contraction is a C number, or is it generic feature? Was that your question, or it is something to do with the fact that it's a free field theory?
My question is that the commutator is C number for only free particle theory.
Good. Yes, because okay, let me clarify. Thanks for bringing that up. Remember, Week's theorem, which I will prove, I'll sketch the proof today, is a way of relating time-ordered product of operators to the norm-ordered operators, right? And time ordering is possible only if you have a notion of time, obviously. So time ordering requires you have a set of operators which knows about the time. And then norm ordering, if you think about it, is a rule to organize creation and annihilation operators. And not all operators will be written in terms of creation and annihilation operators. Right? I can write a random operator if, say, from field theory. Okay, it has nothing to do with creation and annihilation operators. So in one special context where an operator can be written as a linear combination of creation and annihilation operators are free field. So basically, oh, thanks so much. I think it was 1911. And still, right. So therefore, in our context, whenever we talk about the normal ordering, we have in mind the free field. Okay, which is the one particular example where we can write the field operator in terms of creation and annihilation operators. Okay, so manifestly, therefore, we are doing perturbation theory, as we all know. And perturbation theory, the base is free field. So time ordering written in terms of normal ordering in the context of Week theory. So we're already thinking about free field. Then free field, if you now do have a contraction, it is a C number for sure. Okay. Or any operator that can be written in terms of creation and annihilation, and then you can try to compute the commutator. It is always commutator of a creation and annihilation operator, which is always delta function and C number. Does that answer your question?
Yeah, sure.
Good. All right. So last time I wrote down the expression for Week's theorem, and then but I forgot to define the notation. So let me start by defining the notation, and then we will continue. And it appears. So right. So the first is we talked about contraction like that. Okay, and another notation is, for instance, if I want to write down phi 1, phi 2, phi 3, phi 4, for instance, hopefully you understand my notation. Whenever I write down this, I mean like phi x 1, for instance. Okay, and for instance, if I want to have this expression, this is not an operator, right? This is a C number. So this one doesn't need to live inside of normal ordering because that applies to the operators, right? This is manifestly staying at phi 1, phi 4, and then phi 2, phi 3, phi fraction, or you can move to the front. So whenever you see this side of notation with contraction inside of the normal ordering, this is basically just a simplified notation for this sort of expression. Okay, because it doesn't matter. It's enough we can take out of the normal ordering a symbol. Okay, so with that being understood, now let me state the mixed theorem and then let's quickly go through the argument why that might be true. So if you have a chain of time ordering, and then that thing is the same with that this can be written in terms of normal ordering, which I can write it as, and then the rest. By rest, I mean the difference between time ordering and the normal ordering, and that is the same as one contraction, two contractions, maximum contractions. And then I'm gonna write down example expressions. So for instance, what I mean by all one contractions. So here, for instance, we have that. Just to illustrate the point that everything has the exact same coefficient, which is one. Let me write the second term. For instance, it has all these contractions, meaning there's only one contraction is made. The two contraction are hopefully not manifestly clear. I have this. I can have that, and so on in the first. And then maximum contraction. So this means that for n equal to even, so 2k, that means that there's gonna be k contraction. On the other hand, if n is 2k plus 1, that means there will be k contractions, meaning 1 will be left over no matter because the contraction part is an even number. So that is the statement. Now, here's a quick way to go through how this might be true. So this is by induction. So the base point where we already broke down this, we have shown that this is equal to phi 1, phi 2 plus contraction. So I can put inside of the thing just to be consistent with my notation there. Okay, it doesn't matter whether I put in or not instead of the normal ordering symbol. So that is true. Hopefully you remember what I said about this, right? You split it plus minus this. You observe that 3 out of the 4 are already in order. What is that? So you have to flip the order that splits up the commutator, right? That was this contraction. Okay, so then let's assume this is true. So let's write the right hand side of that thing according to formula. Let's write it as W symbol. So this is weak expression. Okay, the weak expression, which is its right hand side. So suppose that is true for n minus 1 point. So that means that I assume that this is true. N minus 1. The W of phi 1 to the phi n minus 1 means it's a complete normal. Hold on. It has a completely normal order of the piece, and then 1 contraction, 2 contraction, and so on and so forth. Right? That is my notation for this W or column for W. So then now let's move on to the phi n case. So let's add another case. So then we have to show that the goal is to show that therefore with that this is also true with n dimension. So that is the goal. Let's see how that goes. Now so let's take a set of n operators. Okay, so you're given a set of n operators. Here and here both, because this is under the time ordering. This is entire expression under the normal ordering, including contraction part, right? I argue that you can put an entire expression under the normal ordering symbol, right? And inside of this normal ordering symbol, again, you remember that the ordering, the way you write down that expression doesn't matter, right? Because there's a concrete relationship you have to follow. Good. Now then, suppose you again you're given an AND operator, and then you just order those operators according to time. Okay, and then suppose so what I'm saying is that suppose somebody had you an operator which is n number of them, and then you figured out the time ordering of that thing, and you just relabel the name. Okay, the one with the largest time, you just call it a by one, which may I don't know by j to the fourth, I don't know, right? You just figure out the time first, and then you just do it according to. I'm just writing random numbers here. Just explaining the concept. This is the first, okay? You know what I mean? So n that the operator given, you sort it at the time, and you just relabel the name according to one to the n. I say, okay? So this is according to time. You can always do it. Is that clear? What I just said? What I just said here? Okay. So then you know that you can pick any n minus one number of them. And for those set of n minus one number of them, this expression is true, right? That was the assumption. That means that you can say that by 2 to the pi n minus 1, you know that it works. First of all, good. So now the goal is to write down the corresponding expression, including pi 1. But now it's easy to write it down. So now time ordering of pi 1 to pi n is the same because you just nicely label the name. Okay. Which you can always do. So I don't lose any generality in doing this, right? So then I can write it as pi 1 over plus, pi 1 over minus, and then I know that this is equal to W to that. So let me remind you this thing totally counterintuitive is annihilation, and this is creation, right? So the second piece, that piece, so let me just rewrite again. That thing is already normal ordered. Right? Yes.
I'm just wondering why the time ordering of phi 1 to phi n equal to, where is phi n?
Oh, here.
Ah.
Now you see?
Yeah.
Yeah, good. So right, it was there all the time. Good, thanks.
Also there, yeah.
So exactly. Thanks. What am I saying? Okay. Done? Very good. All right. So so far so good. Then this term, which is not norm ordered, I can write it as norm ordered piece, which is W by 1 plus done, but that should be equal to that, which means that I have to have subtract that thing. So that means this. Okay, good. So then everything here is norm ordered, right? So now all we need to do is stare at this until it is convincing to you. All right, so let's take both. Stare at this, and basically you need to convince yourself that it is equal to. Okay, so you ready? We're gonna stare at this until each of you are convinced. Start. If it takes 15 minutes, it will take 15 minutes. I walk out after the class. You think I'm joking? Yes, I was joking. So let's actually do it. So now let's first understand this piece. Okay, so this piece has a completely normal ordered piece, right? So that means that this two piece includes completely normal ordered piece, not including pi 1. Okay, so that will be something that looks like this. This space also include all possible contractions, but excluding phi 1. So that means that this space include every possible 1, 2, blah blah contractions, but never including phi 1 contractions with equal coefficient to 1, 1, 1, 1 everywhere. Right? So therefore, what this space includes is a completely normal piece and then all possible contractions, but doesn't include phi 1 with it. Good? Now what does this do? This is a commutator where always at least the phi 1 is involved. Which means that this will give you contraction with the phi 1 involved. And then something else. But that something else never be phi 1. So it will be either from phi 2 to the n. So this will be a 1 contraction including phi 1 if it is a 0 contraction here. 2 contraction with phi 2 if it had 1 contraction here, and so on and so forth. Until it completely saturates. Got it? So overall that means this includes everything that I will explain by the video. Okay? You might say, okay, sounds about all right. And this is authority that can say no. Okay, I'm not so 100% happy. There's a way to sort it out, right? Work out 4-point function, work out 5-point function. At some point, at that point, you will totally convinced. You see, you might say, oh, that doesn't make any sense. I just checked the 4 and 5. Why are you saying that I'm totally convinced? Try it out. You will totally convinced. Okay, so combine that explicit exercises, okay, that you see by every single line, together with abstraction level like this. That combination will make you totally happy. So you just got only 50% of that. We have ever seen a single thing except this. So try it out. That is the weak theorem. Any questions? Yeah. Okay, so we will continue the construction of correlation theory. And so the next topic is what is called in this book by Coleman as Weak diagram. So we're gonna play with the Weak diagram, and then we will derive a master formula. Very important master formula.
So can you recall the relation?
Where does now come from again? Oh, here, yeah. Okay.
Can you recall the relation between the commutator and the contractions?
Can I recover the expression of that thing with the contraction you said? Was that your question?
What was the exact relation between
This and contraction.
Yes.
Okay, good. So let's just look at again like 2, 3. Okay. Okay, you see, you have to see by eye. So phi 2 plus phi 2 minus phi 3 for now. So you learn that the one way to the way you do the commutator first of all is this. This. So far so good? Good. And then this thing contains a non-zero contribution only if I take from phi 2 minus this. The other piece is 0. So that can be written as phi 1, phi 2 contracted with the phi 3 lateral. Here too. So the only piece that is non-zero is only if you take the minus piece from here, that will be written as 1, 3 contraction. Right? See, your level of now happiness went up immediately. So that's how this is gonna work out, right? So it always gives you a contraction when phi 1 is already involved. Okay, and then I can freely add on top of this 4, 5 contracted twice like whatever, right? They will be just going for the right, the same. So it will just appear with that. So 2 contracted is. If I look at the 3, another contraction, 3 contractions, and so on and so forth. Okay, questions. All right, so let's continue. Now we're gonna talk about the weak diagram. but more crucially, we're gonna derive a master formula. There's kind of another master formula, which I used to call master formula of perturbation theory. So this is the precursor of that. Okay, so that master formula looks complicated, very nice, but hard to understand because there's a combinatorics issue. Let's see if I can go through that with you. So let's first talk about the Wick diagram. So for the purpose of this discussion, I'm just gonna take explicit example, right? So I'm gonna take this explicit example where I have one scalar field, real scalar field, and then I have one complex scalar, like that. Okay, and then I'm just gonna write down the interaction between these two. It looks like this. So this is 3-point function, and then diagrammatically, which I will introduce, I will use solely the line for size, and then I'm gonna use the dashed lines for phi. Okay, so soon you will learn how to make a distinction between phi dagger versus phi. You will see. Okay, so I'm gonna take this as an explicit example to illustrate all these points. We're gonna derive a formula which applies to every possible probability. If there is like random expression. So we're doing perturbation theory. Okay, so what is the diagram? So for that matter, recall we talked about the following formula. So we are interested in asking question of scattering properties. There's some number of particles in state, some number of particles in out state, and then we talked about the fact that this can be written as unitary S operator, and then that unitary S operator comes out to be the same as interaction picture time evolution operator that runs from -infinity to or -infinity to plus infinity. Okay, and using the Dyson formula, this can be written as time ordering of exponential of -i, then -infinity to infinity, and time integration of interaction Hamiltonian. Remember, what was that? Once again, if I had if I had a total Hamiltonian, which can be written as h0 plus h prime in shredding the picture. Remember that was nothing but h prime. This, right? Good. So far, so good. And then I also introduced Hamiltonian density. So I can write this as integration over space of density. So from now on, we're going to stick to this expression. And the goal is to learn how to compute this, right? And remember, it's good to have this expression because now I have notion of expansion in powers of interacting Hamiltonian. All right, so let's look at it, and then let's learn some physics out of it. Okay, good. So with that expression, with this example in mind, now let's look at the second order. So S operator include to its second order in perturbation theory, -ig squared over 2 factorial, because I'm doing the expansion of the exponential, and then you go x1, x2, then time ordering. So I just move the time ordering in. That has side 1 dagger, side 1 by 1, side 2 dagger, side 2 by 2. Okay. So I spend the second order in this, with this as my interacting Hamiltonian density. Okay, so I will have 2 factors of this inside of the time ordering symbol, which I have written down. Remember, subscript means x1 versus x2. Okay, good. Yes.
We need to perform a Legendre transformation to do so, right?
Good. Yes, do it, and this will turn into in H prime. You're right. So now I just assume that every one of you are excellent quantum field theorists. So that has done already. When I walk from here to there. Good. Any other question? Okay. So let's look at this. All right. So then this one includes many contractions. We talked about, right, by Wick's theorem. So this says everything everything, just purely no order. Let me just write down a couple of them here. Okay. So one of the piece that is included there. From now, at least for the next 30 minutes, I'm gonna write a bunch of example this thing. So this includes that with now it includes normal. Okay, and then this will include that, and then guess what? It's too much. But it was like everything. But there's a reason why let's not write this much. That. Okay, so you know that these are included in this time ordering according to Week's theorem that we just did. Okay, now we're going to invent a diagrammatic representation of this particular operator, right? This is an operator, right? So for instance, we are working at the second order, so that means that there is a 2 point x1, x2, and then in the rest of the lecture, I'm just going to write in 1 and 2, just to save some talks. And then at each point, x, there are these 3 particles coming out, right? So, for instance, this. So I'm going to label with in arrow for psi, out arrow for psi dagger. So I'm going to do first today. Psi. And then I'm going to, as I told you, I'm going to use dash line for phi. And whenever I do see this contraction, I'm making a connection which goes through. So for instance, this piece, this operator is represented by this diagram. Okay. So by just counting the number of points, you know what order in perturbation theory you are doing, right? There's 2 points, which means that you have to expand the second order of the exponential, and so on. So let's keep doing. Let's draw all these diagrams for now. No brainer. Let's do it. So that thing will look like phi 1 dagger, phi 2 are contracted. Okay, so let's see if I can do it. And then phi 1 that should come out. So come in like that. Oh no, I made a mistake. Like that. So this is phi. This is phi 1, 2. Coming in side, coming out side dagger. Coming up side dagger connected with the side. Right? Okay, keep doing it. 1, 2, and then arrow reversed. Right now, here, side 1 dagger, which is coming up, has not been contracted. Let's keep doing this. So what about this? Then is everybody connected. So like dot is connected to dot, that arrow connected to that arrow, the first arrow is also connected. You can do it. Okay, now you can ask, what about, for instance, before we start making a physics interpretation of that thing, let me ask, what about this side? So there's one coming out, one coming in, one coming in. What about that? I heard something. Say
0.
0. Where does sound come from? Where is it? Where are you? 0. It is 0. Why do you think it's 0? So here is the suggestion. Okay, so this is represented. So now, in order to answer that question, presumably you have gone through to converting this diagram into construction language. That's great because this is not a one-directional thing, right? You can draw and you know how to write down the associated with the construction diagram. Let's do it. So 1, 2, so dot dot. Let me first write this chain. We'll have to write this way. And then, you know, error that comes out, which is dagger or guide, error that comes out from 2, that's dagger or guide, that's this contraction. Right? Okay, so we can ask, why, like there's a phi, and phi, we know that's not 0, in fact, that's like this. Hopefully, you know what I'm writing. I'm writing equal time computation relation, so whenever I write down this, I mean this. Okay? We talked about this. There's a time slice, there's initial condition, blah, blah, right? All spatial like surfaces can be made to the time slice by Lorentz transformation. We talked about all of that. Now, what about for these complex scalars? Sorry, are you? No one said that. This, right? Okay. So for complex scalar, this is for real scale. For complex scalar, remember what was the rule? So we had 2 languages, one in terms of causal initial conditions. Another language is a no-brainer. For given field here, I'm just gonna derive associated conjugate momenta, and then P, Q, I'm just gonna write whatever, right? So this is PQ. For complex field, I have a psi and a psi dagger. And then I have gone through the discussion that you can basically treat these 2 separately, independently, because it gives rise to the same answer. If you're curious, go back. So then, if I want to look at the psi part, I just need to look at the it's associated momentum of that thing. But you see, so associated momentum for psi was what? Psi dagger. Right? Good. So that is not 0. Likewise, if you want to look at the psi dagger, then you want to look at the conjugate momentum of psi dagger. That was what? Psi stuff. The rats are 0. In other words, in the language of contraction, yes, you have a non-zero phi 1 phi 1 contraction. Psi dagger contraction can be non-zero. Psi dagger psi contraction can be non-zero. And you do this as each of these language. Right? Take the psi as a variable and the conjugate variable. Take this as a variable, this is a conjugate momentum, right? But then the rest is 0. In particular, this is 0. Psi dagger is 0. Right? And that's why this was 0. So I'm just explaining one thing for all slowly in detail. Okay, now let's talk about the physics. Any questions so far? Okay, so later on we're going to talk about the Feynman diagrams. So this is the Wick's diagram, and practically they're the same. Okay, especially according to what I'm going to talk about now. Formally, there's a slight difference. For instance, Wick's diagram is associated with this operators, and Feynman diagrams for transition amplitude, meaning just look at the vacuum expectation value of that. Wick's diagram is in position space representation. Feynman diagram is Fourier transfer back to the momentum space, so you're gonna get a diagram in the momentum space representation. But other than that, okay, so it's basically practically the same. Now I will tell you how to extract the physics process out of this thing, which is more or less clear. But let me see if I write down something if it already makes sense to you. If so, that's great. That will save the 10 minutes. If not, that's also great because I'm then just okay. So I'm gonna erase this part and then I will give you physics interpretation of these processes. So from now on, I should be careful. I should be careful for 2 reasons. One, I shouldn't erase this thing because I'm gonna need these expressions many times. So I don't want to write that again. Second reason why it's dangerous is which I will explain later. So let's pick up this first diagram. Okay, so here's one diagram, and this single diagram can describe, in principle, like 4 different processes. So suppose n. So here's a reminder for you. First of all, real scalar field. Here's a super schematic writing, but hopefully that makes sense to you. A diagram, right? That's completely clear expression to you, right? Okay. And then psi is like alpha beta diagram. And then psi diagram is like beta alpha diagram, right? Good. So this is capable of creating a this is capable of creating creating an antiparticle, but destroy a particle. Remember, this carries a charge. Yet this can create a particle, but this can annihilate an antiparticle. Okay? This does the same thing because particle, antiparticle are the same here. Good. So now, with that understanding, I'm just going to write down what this process can produce. And I'm going to call a particle, in this case, to be N. So this is the particle name, which is controlled by alpha operator. And then I call the name N bar because nuclei, historically, which is controlled by beta operator. Is that clear? Yeah. Good. And then I'm just still use the phi to denote the particle or antiparticle that is controlled by A operators. Good. So let's look at this particular diagram first of all. Okay, so that's literally label what? 1. Very good. So this guy can be used several different ways. First of all, if I interpret that as time going upward, meaning now I view as this time, then the claim is that this time it describes the process where N collides with N, and then N comes out, N comes out. Exactly. So some of you should say, what? What are you talking about? Okay, but let me play to mathematically confuse you. That's funny. So the second time, let me say the time goes downwards. So now I'm saying I'm gonna use this diagram this way. Then the claim is that this time it describes N bar goes to N bar. If you are confused with this, you're totally lost here by now. Probably even not that. So now let me use this way. So this time it will describe N colliding with N bar and then goes to N bar. Random choice almost. So now let me clarify. Unless it was already completely clear to you. So why am I saying this? I'm just gonna say one thing for all. So listen up. So let's look at the single vertex with this derivative attached. And then I assign an arrow, which you can think of it as a charge fluid. Okay, so there is a charge fluid because this guy carries charge, say -1. This is the opposite charge of that, say +1, for instance. So this is sort of charge fluid. Now I'm gonna assign a momentum fluid, and depending on the momentum fluid, okay, the same operator does the opposite thing. So carefully listen up. So let's first look at the case where all momenta come towards the vortex. These are the momenta. Okay, so let's give the label. The labeling was that the one that comes into psi, that comes out in terms of charge fluid, psi bar, and phi. So here's the interpretation. There was a particle which was moving like that sinked into the vertex and disappeared. Right? That's the picture physically. Okay? There's a particles flowing, and then boom, they disappear. Which means that at this point, there is an annihilation of the stuff that comes from these field operators. Annihilation happens. So in other words, so let's look at the psi. Psi can annihilate what? N. Yes? So right thing to say here is that, let me use other chalk. So annihilates and destroyed. Okay. So here then, let's see. Psi dagger can annihilate n bar. So in this case, n bar annihilated. Here, 5 annihilated. Okay, let's do the exact same diagram, but with assumption of opposite momentum. Right? Now I'm saying, assuming that I will interpret this diagram with all momentum coming out of it. So something has created at this vertex. Now, psi can create antiparticle. Psi dagger can create what? N. And create. Yeah. And this 5 here. Here's the option. Given a diagram, when I say, oh, time goes up, down, or horizontally, basically I change the meaning of the momentum flow. Okay? And then I explained to you that different momentum flow with the exact same diagram has different physical meaning to it. And simple pneumatics is that if the momentum flow is the same as the charge flow, it is n. Okay, let's check. If it is a momentum flow is the same as this, it's n particle. If the momentum flow is opposite to the charge flow, it's the antiparticle. Let's check. If the momentum flow is opposite to that, it's antiparticle. Okay? And for real, it doesn't matter. It's the same thing. Now you're ready to now follow me to interpret this. Okay, so let's look at this. Let's travel up. That means there's a momentum going in, which is the same direction as the charge flow. So n collide and comes out because this is time direction. Momentum comes out of that. And again, momentum is the same as the arrow, therefore n come out. Got it? Now let's back to the backward. Now, if time goes down, then this is the momentum flow, which is reversing or going backward to the charge flow, so and Bryan line. And then coming out, again, momentum flow is opposite to the charge flows and come out. You got it? Okay, now finally, let's do this. If I go to that, because time goes that way, this is, in this case, that psi is n, this is n bar. Yeah? And then converted into phi, this is now n, this is n bar. Got it? Okay. So now let's quickly kill this. Yes.
You said that there are three meanings,
Yes.
and you said that all these three meaning has physical meaning.
Yes.
There's no clear, just one. There is no just one clear.
Yes. Because if I just draw this diagram, I haven't specified the momentum yet. And I haven't specified the time fluid direction yet. Okay, the single diagram, which is true for Weeks diagram, but what I'm doing here is really what you will do for final diagrams, because I talked about momentum assignment, right? And so single diagram, depending on the momentum assignment, can describe in principle these three possible properties. And it is known as crossing symmetry. We will discuss that at some point. Meaning, single diagram, you can look at that way, or the other way around. Okay? And why three? In two to two processes, there's only three different Lorentz invariant momenta you can define. So anyway, we'll talk about it. Don't worry about it. So for now, you just
Can you clarify the what? So you said three kinds of different time direction, but why don't you introduce the left?
You can do it. So here, let's do it. Then you get again n bar goes n bar. So this is the same kind. So in principle, you can work out all of that. But what I'm saying is that given four momenta, you got it. Given four momenta, there are three Lorentz invariant quantity we can define. which is what's known as the model from there. We will go through that, so don't worry too much about it. Here, enjoy, okay? You just start getting some physics out of it. Let's do this quickly. If a time goes up, phi goes to n bar n. Here, phi collided with n, and then phi n comes out. That way, phi n bar goes to phi n bar. Three processes. Okay, sorry, you can look at this way too. Then it is n bar, sorry, n bar goes to phi. Okay, so in principle, we can look at all of that. What about this weird looking guy? So for that, I've been invoking asymptotic time, right? We talked about asymptotic state, meaning if I go all the way up, okay, this interacting Hamiltonian state asymptotic to free looking state. We talked about all that. Now let's do boom. What do you see? What do you see? Nothing. So at some characteristic sign, asymptotically you have nothing. There's a nice name to that nothing. What is that? Vacuum. Okay, let's do the same thing for the future. What do you see? Vacuum. If you change time direction, the same. Vacuum, vacuum. So this describes the vacuum transition amplitude. Okay, you start with the vacuum. Quantum mechanically something happened, like particles created spontaneous out of the vacuum and then killed themselves. And then you left with the vacuum. So this is the vacuum transition amplitude, which will be extremely important. Another thing that I want to say, these are tree diagrams, manifestly. I'm not manifestly, probably. I'm totally prejudiced. Does this look like a tree to you? Not at all. Okay. Does this look like a loop to you?
Yes.
Loop?
Yeah.
No? Okay. Are you open-minded? This is a loop. These are tree diagrams. Okay. And this course, we're gonna learn how to compute tree diagrams properly. Loop requires a little bit more muscle. Okay, you need some techniques to do so. So that is the topic of the second part of the video. Anyway, so again, already you learned a lot of stuff. Now, so that's so much about the physics interpretation. Now, you see hopefully that each of this term that come from Wick expansion. So we start with the Dyson formula, and we did a perturbative expansion. We use the Wick's theorem to make the expansion, right? So this will be called Wick expansion or Dyson-Wick expansion, depending on how you like to call. And this part of the discussion is to show that each of these integrand is one-to-one to give a specific diagram, right? And then you can even do the other way around. Now the question is, as a whole, so this has a lot of stuff in it, right? There's exponential, okay? Can I say uniquely, what does that correspond to in terms of sum of diagrams? You might say, can you just keep doing this? Yes, you can keep doing this. There's a subtlety. Otherwise, what are we discussing here? Subtlety is simply this. If you have n vertices, in this case, we're talking about two vertices. If you have n vertices, okay, naively, so then that n vertex thing has all kinds of contraction with it, right? If you have n vertices, naively, you can permit all those n vertices. You can like rename what you call 1 to be 2, what you call to be 2 to be 3, and so on and so forth. But then naively might say, oh, I simply compute the n factorial diagrams. Don't bother me. If you have that mentality, great, go do it. If you are scared about the n factorial stuff, follow me. Okay? So the answer to that is that we don't have to deal with the entire n factorial. That's first thing, nice thing to do, right? So we don't have to deal with the entire n factorial. Two, in order to understand that, anyway, you have to understand n factorial, first of all. But once we go through the derivation that I will discuss now, then we will have a compact, nice formula, which is true for entire S operator in terms of a diagrammatic representation. Okay, so that's the master formula that I mentioned that I will discuss now. Any questions? Yes.
For diagram 1, can we like bend the left two tree branches to like make vacuum goes to n bar?
Good. Yes, you can. In principle, you can interpret that as like you bend like that guy. Okay, so like anyway, your arms and foot all like that. So then there's a vacuum and then go to the 4 particles. Okay, so that is acceptable interpretation. The only problem with that is that out of the vacuum, which carries 0 energy and momenta, you create something that carries a lot of energy and momenta. So energy momentum conservation will be set. And you will eventually have a automated machinery that whenever you have a diagram or physics interpretation that violate this energy momentum conservation, it automatically will be 0 too. Just like when we try to compute the contractions, there's a built-in thing that tells you it is 0. Good question. And then, yeah, there was a question.
I think it is a little bit difficult to clarify. When you write down the blue arrow, the blue, why those are the 3, the arrow is point in the centers, or why those are the 3 arrow point out of the direction?
Oh, you can do whichever way you want in principle.
Oh, really?
Yeah, but then once you know creation knowledge apart, like for instance, let me flip that way. Right? So that means like that. So that means this will annihilate, this will create, this will annihilate. Again, you can just look at this thing and you can read it correctly. So in this case, n bar is annihilated and the n bar is created, right? And then for instance, phi is annihilated. So in fact, that was happening here, right? So if I read this diagram as like that, I'm sorry, yes, like that. If time is that way, this momentum flew in, that momentum flew out, right? We already have done that in essence. Okay, so it's not necessary that you only read it that way. You can do whatever error you want. But I'm just telling you what's the rule to understand the business meaning of this.
Okay, thank you.
Yeah.
Or those diagrams just like mathematical devices to track the contributions from various terms, or
That's
like
correct.
it's like ontologically, do they really be created and annihilated and vacuum comes out like?
Yeah, so good. So you can do cold-minded mathematician and to like just take this, don't bother with the weird looking diagrams. I'm just gonna do algebra carefully. You can do that. And then you can just interpret every single this operator, but with the physics with it. You see, already it's less clear. Okay, contraction is momentum, and which one is created, which one is died or shed, right? If you look at that, with the 5 minutes of discussion, you're ready to start reading the physics out. So there's a benefit to it, but I'm not saying it's impossible to do from this representation. You can just stick to this algebraic expression and then try to extract physics out of it. Certainly it's possible. And the claim is, as you said, it meant to be like different representation of the same mathematical expression. And sometimes it is more intuitive to use this mathematical representation to do the physics. But again, that's not just must, but happen to be useful. And higher order theories always draw this Feynman diagram. They write down normal ordering up. Have you ever done that? I've never done that. We will draw this million times, like not single time writing. That means this normal. No. Once we learn this, let's go. There was a question.
괜찮아. 해결했습니다.
Okay. Yeah, good. So let's do it. I should be careful again. So I'm gonna read all this part, but keeping this. Make a point. Okay, so now let me make a couple of comments, which will be important ingredients. So comment number 1. So from that weak expansion, generate would work or includes. So the comment number 1 is this weak expansion, meaning if you just write the time ordering in terms of this, automatically generate all possible permutations of vertices. Okay, so now in order to clarify what I mean by this expression, let me define. I don't have to use this fancy format. Okay, it's a shame. Let me not do it. So let me just following this call a pattern, or actually you will hear more people just talk about topology of a diagram. So what is the pattern of diagram or topology of diagram? First of all, weak diagram is defined modulo topology only. In other words, this thing can be written. Okay, let me take this example. I can draw this way, or I can like flip up and down, or I can just flip sides that way. Doesn't matter. Okay. So diagram, so long as it includes all the vertices in correct nexus, all that, that means the same diagram. Okay. So weak diagram is defined modulo topology. So then you see that so at fixed order in correlation theory, in this case second order, that then includes a lot of different topologies. Different looking diagrams. For instance, there's this guy, which does not look at all like these two. Of course, these two are very different from that thing, but they all come from the second order correlation theory extension. So I would call this is a class of pattern of given topology of diagram. This is another. Let me actually box it. This is the second kind of topology or pattern, and this is yet another kind of topology, which are coming from the same fixed order in correlation theory. Okay? So now let's observe it. And now, in order to make this point, let's look at the second kind of diagrams, second topology. You see, if you look at this is almost the same, except error rule of error. And in fact, this one can be rewritten as follows. The second diagram I could have written as two, one, right? Right? So that means that this is related to the first one by permutation of vertices. So the first point is that for a given topology of diagram at fixed order in N, okay? This weak expansion automatically spits out all possible permutations, but almost. I said almost. Why is that almost? So for that, let's look at this one. So this is one example. Okay, so if this were to be a true statement without even this fine print of almost all, that thing also should create the following diagram too, like 2, 1, separately once each, right? But you see, this is basically exactly the same diagram as that. Not even different, any different. So then this one would not fit out this and that separately. Because that corresponds to the exact single contraction. How can I do this two different ways? There's no way. Okay? So that's the one of the subtlety. You see? So if I naively say, oh, can I get n factorial diagrams? No. Because of this fact, which I will make more precise, we can expect it will not just generate n factorial different diagrams. So in order to make this point right, so we will define what is known as symmetry. So let me call a diagram, given diagram. Here's the notation. The diagram with n vertices with given pattern. This is pattern at order n order. So for instance, n is 2, all of that. This can be like first, this is one kind of pattern. This is another pattern. This is yet another pattern, for instance. Okay, so this is my notation for a diagram with n vertices and then a given pattern. This can run from the 0, 1 to 3, whatever, different kind of patterns. So then I can define a symmetry factor as symmetry of diagram. So this is the number of permutations of vertices that leaves the diagram invariant. For instance, in this example, symmetry factor is 2. You can do the one permutation. There are 2 diagrams, therefore. So that number of permutations. Okay, so if you like, what do you want to say? So here, the symmetry factor is 2. There are 2. Is this 2 permutation? Do you call this 2 permutation? Yes, it is 2 permutation, right? 1, 2, 2, 1, 2 permutation, and they look exact same, right? So therefore that's correct. So the number of permutations that live that doesn't change anything. They look exact same diagram. Okay, and so that's the thing. And here, let's take another example. So there's a slide in here. So that diagram, symmetry factor is 2. Let me make another diagram. This is blue. And so let me call 1, 2, 3, 4. So there are 4 diagrams where the vertices along the chart flow goes like 1, 2, 3, 4, then 2, 3, 4, 1, 3, 4, 1, 2, 4, 1, 2, 3, right? I can just do the rotation. And none of that changes anything here. So if a permutation of 1 to 3 leaves the diagram invariant, okay, so here the symmetry factor is 4. But odd permutations, for instance, 2, 1, 3, 4, flip the error all of a sudden. And some of the such diagram will be automatically 0, actually. If you just split one of that to naively, the error goes here, goes there. So there is no such a thing. But you can put it all the way in such a way the error goes the other way around. That is viewed as a different diagram as that thing, right? And again, there's a symmetry factor of 4 for those reverse fluid diagram. Okay, so now once you understand the concept of a symmetry factor, so now we are ready to talk about the one first important result. Any questions so far? Yes.
That S equals to 4 example is valid as long as the 4 external particles are the same particle.
Yeah, here, good. Yeah, that's true. And here I'm explicitly thinking of this particular example where, yes, all 4 legs are the same. That's right. Otherwise, the symmetry factor can be different. That's right. Another question. Okay. Good. Is it a good idea to good. So let me say one more time before I erase. Week's expansion automatically spits out all possible contractions, which include different topologies. We need a topology, right? Some number of equivalent diagrams, but sometimes exactly the same diagrams. When it is exactly the same diagrams, we define a symmetry factor. Did I almost say symmetry defect operator? Symmetry factor. Okay, now let me say one more thing before I move on. So Dyson's formula includes the integration over all the vertices. Okay, so I'm making yet another important factor. So I'm going to combine all this factor to derive a formula now. So this is inequivalent to that as an integrand. So as an integrand diagram, this is different from that. As an integrand diagram, this is exact same as that. That's when we talk about symmetry factor. However, as an operator included in this as an operator, this will have the same answer as that. Because x1 and x2 are dummy variables, I'm just going to integrate all of that. So statement, another statement. Take a diagram. Get inequivalent integrand diagrams by doing permutation of the vertices. Those will result in the same operator once you finish integration over axis. So there are 2 combinatorics we talked about. Okay? One, fix the topology. fixed topology. Within the US, how many inequivalent integrand diagram you might get? Naive answer n factorial. Right? Naive answer was n factorial. I showed that in some cases there's a symmetry factor s. Therefore, you're not going to get n factorial inequivalent integrand diagrams. But you actually get n factorial over s distinct integrand diagrams. Is that clear so far? Okay, there are naively two. Divided by two, that's why you get one inequivalent diagram. Here are two, because they give the same answer, sorry, different diagram. Okay? And then, so therefore, at the level of integrand, let me say that I'm gonna write down formula. At the level of integrand, you get n factorial over s inequivalent integrand diagrams. Clear? However, once you integrate all the axes, every single of those inequivalent integrand diagrams will yield the same operator. Good. Now I'm gonna combine. We will build up on this even more. So give it with me. This is the first important formula. So this thing, let me just write up one option. Let me just write this. UI plus number of vertices, and then n factorial. Good, because I'm expanding this. Okay. Now, okay, let me just write first the S1 or N T. And so I just literally wrote it out. Now I start making the statement I already told you. So this is integrand. I call separate integrand diagram, and this one will have, first of all, given a this is a sum over different topologies. Remember, single time ordering has many different contractions, right? And different contractions give rise to different topology of diagrams. So I have to sum over different topologies. Okay? And then for fixed topology, I told you that there is this much distinct or inequivalent integral diagrams. Not just that. Okay? And then for each of them, there will be contraction of the contractions. So this symbol just means that for the example of this thing was like side 1 diagram, side 1 by 1, side 2 diagram, side 2 by 2. For instance, like and that with that. So far so good? Yes. But there is a non-trivial thing when I wrote this. Why did not so naively explicit expression for contraction will all be different within single distance topology class. But nevertheless, I did not write separate because eventually I'm just gonna integrate over this, which will yield the same operators. I don't care much. Okay? So then that will result in a first important formula.
Are you sure the factorial in the denominator?
Oh, no, I'm not sure about that. I'm sure it's wrong. I erased it. Good. So then this can be written as sum over n, expansion in the perturbation order. Okay, and then there's a 1 over n b factorial. This is the number of indices or vertices of given diagrams that is same as order or same as this number of axes. And then n b factorial s of d times I have minus I to the n dx 1 dx n and then d contraction. So by d contraction, I mean the contraction of operator that give rise to particular diagonal key. That's what I meant. So we're gonna call this thing as operator coming from that contraction. Oh, I forgot the sum over. Sorry, I forgot the sum over topology, different topologies. So here is the first math formula. The Dyson formula or S operator is same as expansion in order in the perturbation theory, number of vertices. And then for each fixed number of order, I have some different topologies. Okay, and then that is same now has there's a with n order and pn diagram operator divided by symmetry. Hopefully now you read this as a map between algebraic equation and diagrammatic representation. Okay, so if you tell me what order you want me to do it, and then I can list possible topology, which topology you want me to look at, you can just specify, right? Different topology means different physical properties. Remember what I just erased. As second order, there are three different at least different topologies. Each of them never interfere because they correspond to different physical processes, right? So different physical processes, and then I can now talk about the diagram. So that is the relationship. Good. So the another level that we have to go up takes a little bit more effort. For questions before I do it. Okay, now we are going to show that this is great, but this is still redundant. Remember, when we go from naivety to here, I already removed a lot of redundancies because I said some of them are basically the same. I don't have to compute separately, right? But then the second layer is that I will show this is equal to oops, I have done that. Okay, so next step we want to go is to show this. So diagram can be exponentiated to get to the even smaller set of diagram. So let me explain the concept and then motivate. So here's one diagram we can look at, for instance. So this will appear in first order in perturbation here because there are 4 vertices, right? And yet this is disconnected diagram. And there's a connected diagram in fourth order too. So one example of a connected diagram in fourth order, for instance, which I draw, which is corresponds to different physical classes on the other hand. So this is connected diagram. Right, so clear. This is everything. So connected means connected, right? Starting from one piece, you can add any other piece without with a continuous movement. This you cannot. But then you may wonder still, if you look at this, I have seen this at second order perturbation theory, and I have computed it. Can I recycle that computation? Looks like yes, you can compute this. Somehow this answer should be product of this and that, which is the same as above, right? So this one has that concept. Okay, you don't have to compute the disconnected diagram separately. So that's the concept. In fact, here C means connected diagram. So if you know that all the connected diagram, basically you can get the entire space of all diagrams, connected, disconnected. Okay, so that is this formula is all about. So, let me see. Okay, I might need like 15 minutes to prove it, which is a little bit stretching, given the time. So I'll stop here, but so next time we will quickly derive this. Actually, carefully we'll derive this because this is subtle. There's yet another combinatorics we have to worry about. But after that, we all almost getting to the point where we start talking about meaningful conversations on provision theory. Any question?
Actually, we are using confusing notation, so
Yeah.
NC and above we have C or so.
Here and here.
Yeah, so above C means the connected and lower is the summation, right?
Lower this.
Okay, and C,
There is NC. This NC?
that is summation of a C, right?
Yeah. This is sum over all connected diagrams. And for each connected diagram, there will be NC indices, NC vertices. Remember, my notation was N vertices with the fixed topology, and then I'm computing things. So my notation is hopefully consistent. Let's see. I'm summing over all possible connected diagrams. This means that this takes care of a topology too. Okay?
So circle one means that the vertices is one.
No, it is just the first connected diagram.
Okay.
And there's second connected diagram and third connected diagram with the possible additional number of vertices.
Then what is the superscript of D? I mean, C. or
This-
D, yes.
This is just to make a distinction between that, because this is an arbitrary diagram, this is a connected diagram. So sorry, yeah, location can be random, so this means it's just that I'm only looking at the connected diagrams. Okay, so for instance, this is a square of that connected diagram. Right, and obviously if you expand exponential, then you get like first power, which is just that single connected diagram. Square, that's product of the two connected diagram, which is disconnected, and cube, and so on and so forth. Right? So you will get to something like this by expanding this, for instance. Now, the only question is whether this is exact correct combinatoric factors. And understanding that is the key, basically. Right? Conceptually, you understand that if you expand it, you get all sorts of diagrams, right? By putting together all connected pieces. Yeah.
So you're calling diagram A and diagram B has the same pattern, even only if they are topologically same up to some permutation of vertex indexes. Could you clarify the same pattern is?
Yeah, good. So by same pattern, I mean, so let me take the example where I draw earlier. So they're in the same topology or pattern, even though they are distinct diagram as integrand.
It means they are exactly same as an integrand up to permutation of indices.
That's right.
Okay.
Right. So fixed topology, meaning you fix out the external legs and internal vertices. And obviously, this is nothing to do with that too, right? This is very different topologies. So fixed topology or pattern. Within that, there can be inequivalent diagrams which are related by permutation of vertices. Sometimes permutation leaves the diagram exactly untouched. Sometimes. That's why we have to introduce symmetry diagrams. And then all of this will give rise to the same operator once you do the integration. Okay, so some layers. So digest it, come back, and then we will cover this quickly and move on. Yes.
And we count the number of Week10 with the right?
Yeah.
Then we need to 그 다른 애들에 대해서 X가 같아야 그걸 해줄 수 있는 거잖아요.
Yes.
그걸 우리가 어떻게 확신할 수 있을까요?
So that's why I have sum over n first, then sum over topology first, and then now I fix the basic everything. The only leftover is a permutation of vertices.
그러니까 그걸 할 때 그 S라니까 뭐 이게 뭐 여러 가지가 있는데
어.
아,
So this is the function of the n and the pn too. Hopefully my explantation clarified it. Yeah.
네,
오케이 그럼 잘 나는데 얘 지금 수업이 있구나. 아 잠깐만 재욱 씨 어디 갔어요? 아 그냥 혹시 레코딩 끝나면 되나요? 모르죠. 아 이거 되겠죠?